So, let us look at it, and the main theorem that this neighbor joining algorithm rests is it is going to help us find the right cherry if your distance matrix is additive. Okay. Because when we started talking about additive phylogeny, right, we said that okay, let us initially look at an algorithm that will figure out what are the cherries, meaning the two leaves which share the same neighbor, right. So, these are the cherries, right. They are called cherries like we said because they look like cherry fruits hanging off a branch. So, if you have a tree like this, these two are cherries because they have the same common neighbor. These two are cherries because they again have the same common neighbor. This leaf and this leaf are not part of any cherries. Okay. So, but this leaf and this leaf forms a cherry, and then this leaf and this leaf forms a cherry. Okay. These two leaves are not forming a cherry. Now, given the input distance matrix D which is additive, given an additive distance matrix D, can we correctly find a cherry? Okay. So, that is what we are going to look at. We have seen that if you look at the minimum entry in D, right, the smallest entry or smallest value in D, that does not correspond to a cherry, because we looked at this example of this 100, 1, 1, 100. The smallest entry is going to be between these two nodes I and j, but that is not forming a cherry. So, that is like length 3, all the others are 100 plus all the other pairs, but this is not forming a cherry, right. So, but then we need some kind of an elegant way to figure out a cherry even in cases such as this, right. So, let us see how we can do that, and that is what the main crux of the neighbor joining algorithm is. Okay. Finding the minimum entry in D does not work, but can we get some other matrix D in which the minimum entry corresponds to a cherry. Okay. So, that is the idea. So, for that we are going to take a distance matrix D and we are going to construct another matrix D star, is going to transform D to D star, so that the minimum entry in D star will form a cherry. Okay. So, given an n cross n distance, and let us see how we define D star. Okay. Given an n cross n distance matrix D where you have n leaves or species, right. So, this is n cross n, its neighbor joining matrix, this D star is called a neighbor joining matrix. Okay. It is going to join neighbors together, as the neighbors are going to get the smallest value there. Okay. So, is the matrix D star or the cherry is going to get the smallest value there. It is going to be its neighbor joining matrix is the matrix D star defined as the following. Okay. You get D of I j, right. So, this is the distance from I to j, you multiply it with n minus 2 where n is the total number of leaves, right, and then you subtract the total distance of I to every other leaf, and then you also subtract the total distance of j to every other leaf. Okay. So, total distance of d of I is the sum of the distances from leaf I to all other leaves. Okay. So, that is what this total distance d of I means, and total distance d of j means it is the distance from j to every other leaf. Okay. We will just see an example shortly, and this is a weird looking transformation, right. So, I mean you are taking d I j and you are multiplying it with n minus 2, then you are subtracting the total distance of I and total distance of j. I mean why are we doing all these transformations, and then we are claiming that the smallest entry here will be a cherry, right. I mean we are doing all these transformations to ensure that the smallest entry is a cherry, but then it is very opaque, right. So, why should this transformation convert a matrix D where the smallest entry is not a cherry to another matrix D where the smallest entry is indeed a cherry. Okay. So, that we need to understand a bit, but let us say that we take that for faith, but at least illustrate what the operation is. Okay. So, this is the matrix D, this is the total distance vector D, right. So, from I to everything else, right. So, I to I itself is 0, j to j itself is 0 and so on. So, all you have to do is row sums, right. You do all these row sums, that will give you the total distance vector, because it is a symmetric matrix, column sums will also give you the same value. So, the total distance that is implied by this input matrix D for I will be 56, for j to every other leaf will be 38, for k to every other leaf will be 46, for L to every other leaf will be 48, right. So, that is what it is, and so you have to subtract that from, let us take one particular entry, right. So, I am not sure if they have illustrated this. So, let me just take one particular entry. Let us take this particular entry, right. So, d star I j is going to be n minus 2, n is 4 here. So, 4 minus 2 times d I j is going to be 13, right, minus total distance of I minus total distance of j. So, total distance of I is 56, total distance of j is 38. So, minus 56 minus 38, right. So, which means that this is 2 times 13 is 26 minus 56 minus 38. 26 minus 56 is minus 30, minus 30 minus 38 is minus 68, okay, and that is what is given here. Okay. So, similarly, you can verify that these other entries are minus 60 and so on. Okay. And the beautiful thing here is that once you do this transformation from d to d star, right, and you look at the smallest entries in d star, which is essentially minus 60, right, sorry, minus 68, right. So, minus 68 is smaller than minus 60. So, all the minus 68s are the smallest entries and they are grouping together I and j, right, and then k and l. Okay. So, let me just erase it and then just highlight the smallest entries alone. The smallest entry is I and j and the smallest entry is k and l. So, what is this saying? The smallest entries in the d star actually correspond to a cherry. So, what we are claiming is that I and j is a cherry in the tree that fits this matrix, fits this D matrix and similarly k and l is a cherry, meaning that they share the same neighbor in the tree that fits this matrix D. Okay. That is what we are claiming, and let us just look at the tree itself, right, and that is the neighbor joining theorem. Okay. So, if D is additive, then the smallest element of D star corresponds to neighboring leaves in tree of D, or it corresponds to a cherry in tree of D. Okay. So, that is the neighbor joining theorem put in concretely and succinctly, right. In this particular case, it is I and j is a cherry and there is also k and l which is also a cherry. Okay. That is what this neighbor joining theorem will tell us. These are the smallest entries minus 68, right. Once you know the cherry, right, then things are easier, right. So, then you can make a cherry and then you can represent that, you can remove the cherry and represent the cherry with the internal node m for which both the leaves in the cherry are neighbors, right. So, then you will have a smaller distance matrix and you can recurse on this problem, right. So, that is what in fact we will do. So, this is the key theorem. So, you convert your D to a D star matrix and you take the smallest element of D star and that will correspond to a cherry. And then you keep on picking these cherries, you remove the cherry and then you have a sub problem that you recurse on, you find the cherry in that sub problem, you remove it, you recurse on further and so on, and then later on you add all the removed cherries and you will get your full tree. Okay. So, it goes very much similar to additive phylogeny where we were removing one limb at a time, here you are removing one cherry at a time. Okay. The proof of this theorem we are not going to see right away. If you are interested, we can do a separate session on that, but we will just take this for faith now, okay, that the smallest entries here will correspond to a cherry. If you believe that, which is true indeed, that people have proved this before, then we can do the following: construct the neighbor joining matrix D star from D, that is the first step of the algorithm. Then you find the element D star I j, that is the minimum element, right. There may be multiple minimums, then you just choose one of the minimums, right. So, there are multiple minimums, you are going to choose one of the minimums, in this particular case I comma j, and then you compute this delta I j. Okay. So, that will tell you essentially what are the different limb lengths of I to the internal node and j to the internal node, because that we still need to figure out, and we have already calculated that before, but we are going to repeat that, because when we initially had this idea of finding a cherry and picking the cherry and figuring out the limb lengths of each of the leaves in the cherry, we use something similar, right. So, you just compute delta I j as total distance d of I minus total distance d of j divided by n minus 2. Okay. And then you can set your limb length to be equal to half of d I j plus delta I j and limb length of j to be equal to half of d I j minus delta I j. Okay. We will We will verify this carefully why these particular formulas arise a little bit later, but just let us go with the flow. Okay. So, this is limb length of I, this is limb length of j. Okay. Then you can remove the cherry and replace it with a common internal node, that will be this node m, and then you need to figure out this for this new row and new column what these entries 10, 11 and 10, 11 are, right. So, that one you can figure it out using this particular formula. You form a matrix D prime by removing the ith and jth row or column from D and adding an mth row or column such that for any k, right, d k comma m is going to be this particular formula. This is again a very similar formula as before. It just comes from the following expression, where you have figured out that I and j are cherries and you know that m is their internal node, right, and then you have some other node. I mean, m has at least one other edge, right, because each internal node has to have a degree at least 3. So, then you go on like this, and there is at least another leaf k, right, in some subtree that is connected to m. M may have some other subtrees also, but at least one such k will be there, right. So, then you are trying to figure out this this business we had before, right. So, you have j to k is this, right, then you have I to k is this, those are these two things. So, this is I to k, this is j to k, and then you have to subtract I to j, right. So, then these parts are removed, then this will give you this m to k, but 2 times you are accounting it, right. So, then you have to divide it by 2, right. So, you have d to I, d I comma k, d j comma k, you are subtracting d I comma j, then you will get this thing in the black box, but you are accounting this green and blue 2 times, right. So, if you want to figure out what is the distance from m to k, then you have to take that this expression divided by 2, okay, and that is how you get this 10 and 11 here, okay, and this is a symmetric matrix. So, this will also be 10 and 11. So, if you change k with L, then you will get 11, if you have k as k, you will get 10, okay. So, this is like a very similar looking expression that you have seen before, right, and so this is how you update your matrix from a 4 cross 4 matrix. You remove I and j leaf and you replace it with the leaf m, which is your internal node, and then you update your matrix using this formula, okay, and that is what is being explained here. So, this is just a flashback because we have already seen this kind of an argument before. Then you apply your neighbor joining to D prime to obtain tree of D prime. So, now we have a recursive subproblem, right, with one less rows and one less column. So, one less number of species, right. So, then you can recursively apply this algorithm, you can get tree of D prime. So, you will get this m, k and L, right. Now, we have to just attach the cherry to this and put in the appropriate limb lengths. It is a very easy process now. So, you just reattach the limbs of I and j to this, and you have already computed the limb length to be this half of d I j plus delta I j and similar formulas. So, then you will get 11 and 2 here, okay. That will give you the full tree, and this is the full neighbor joining algorithm now. You have constructed neighbor joining matrix D star from D. So, that is your first step, you construct that, then you find the minimum element D star I j of D star, right. That will if there are multiple minimum elements, you just choose one of them, right, and then you know that will be a cherry according to the neighbor joining theorem, right. So, then you can compute this delta I j, and then you can set your limb lengths to be this half of d I j plus delta I j and half of d I j minus delta I j. Then you can use this very familiar formula by now. You should know this almost by heart from by now, that if you want to figure out the distance between d of k and m, then you go from k to I and k to j, and then you are subtracting this d I j, and then you are double counting d k comma m. So, you have to divide it by 2, okay. So, this will give you this matrix D, which is n cross n, to this matrix D prime, which is n minus 1 cross n minus 1. So, now you have a smaller subproblem where one row and one column is deleted from D to get D prime. Now, you can recurse on it, you can run neighbor joining again to get the tree of D prime, and in this tree of D prime you know where M is, there you just go and attach your cherry back I and j with the appropriate limb length of I and limb length of j. Okay. So, this is the overall neighbor joining algorithm, and the code challenge is of course to implement it, and all of these are mostly matrix operations and finding the minimum entry in a matrix and so on. So, it should not be too hard to code it up if you understood the flow or the logic of the algorithm. Okay. Let me see if there are any questions related to this. Let us take a moment to pause and think about it. So, let us take a step back now, right. So, the neighbor joining we said is good in two ways. One is that if you provide an additive matrix D, then it is going to work and provide you a phylogeny or a tree, right, that will fit this matrix D, and that is according to this neighbor joining theorem. Okay. But the neighbor joining theorem may not work, or will most likely not work if your if your input matrix D is not additive, right. So, then in those cases, are these operations where we are computing this delta I j and then we are taking this operations, are they still valid? You may not find a cherry, right, if it is a non-additive matrix. You do not even have a tree that is going to identically, perfectly fit the input matrix D, right. So, what guarantee do we have that this this behaves like a good heuristic? Okay. And then that is what we are going to give some intuitions now. Okay. So, the neighbor joining will find the tree returned by neighbor joining on the following non-additive matrix. So, this is the non-additive matrix that we have been having all along, right. So, this is 3 and 5, right, and so there is no tree that will fit this matrix exactly, right. So, this is a non-additive matrix. Let us just run the neighbor joining on this matrix, and then it is an exercise for you to figure out what tree it provides. Okay. And then how does it compare with the UPGMA tree that you have, right. So, is one better than the other. So, you can do that as an exercise. Okay. And you can see that some of these operations, okay, again when we look into the proof of the neighbor joining theorem, it will become much clearer. Okay. So, some of these operations, even if the input matrix D is not additive, this computing this delta I j and then setting it to be half of d I j plus delta I j, right. So, this total distance is not using the distance of I to just one other leaf, right. It is trying to use the distance to every other leaf. So, that is a more robust operation than just choosing one leaf like an additive phylogeny algorithms, right. So, here similarly total distance of d of j, it is going to figure out the distance of j to every other leaf. Okay. So, even if one of those leaves is not correct, because there are these two entries which makes it non-additive, right. So, even if some of the leaves are noisily measured, and because of the noise in your measurement data or on the instruments or measurement instruments and other things, you do not have a perfect, or in your noise in your multiple sequence alignment procedures, right. So, because of that, if you do not have a perfectly additive matrix, maybe it only affects some of the leaves, right, and not all of the leaves. So, by looking at the total distance of I to all of the leaves and total distance of j to all of the leaves, you are trying to make the estimates of the limb lengths to be more robust against noise in a few leaves. Okay. And that is the main intuition on why neighbor joining also works better for cases where you do not have a perfect additive matrix to begin with. Okay. And if you had a perfect additive matrix, you do not have to calculate this distance of I to every other leaf or j to every other leaf, right. So, that we have already seen before, right. So, if you want to, you know that I and j is a cherry. Let me just get you know that I and j is a cherry. This is the M node, and then you have some other leaf k in some subtree that is branching out from M. Okay. So, M may have some other branches also. Okay. So, there may be other branches also. Okay. So, now if your input matrix D is perfectly additive, then I can choose any other k to figure out what these limb length of I and limb length of j is. Okay. So, we were at the point of trying to figure out how neighbor joining works if the input matrix D is not additive. Okay. In order to understand that, let us see if the input matrix D is additive, then what should be the I mean, can we simplify some of these calculations, right. If the input matrix D is additive, then I can take any k, it can be in this subtree rooted at this internal node M to which I and j cherry is connected, right, or it could be some leaf here, or it could be some leaf in the in any of the subtrees that is connected to M. Okay. But let us say that I choose one particular leaf k. Okay. Then if I want to know what is the limb length of I, right. So, then the limb length of I, okay. So, let me just look at limb length of I, the limb length of j is going to be something similar. So, let us just focus on limb length of I alone. Limb length of I is going to be, you will have to look at d I to m, right. So, that is what you need, but then you do not have that access readily. So, you only have I to m and m to k, which is d I k, but then this m to k I do not want to consider it, I want to remove it, right. So, then I can remove it by using d j to k. So, minus d j to k, right. So, that will remove this part, but then it is going to also unnecessarily remove this j to m, right. So, I need to add it back. So, then I can just add d I j. So, then that will add this part d j m back, but this will be counted twice. So, this has to be divided by 2, right. So, this is one estimate of LL of I, and this will work for any k, for any leaf k that is not equal to I comma j, this will work, right. So, I mean, if you have a perfectly additive input matrix D, then any k you put in, you will get the same value of LL of I. Okay. So, average across all k not equal to I comma j, your LL of I estimate, I am going to call it as hat, this is your LL of I estimate, is going to be your best estimate if you want to, if you have a non-additive matrix and you have different leaves k giving you different estimates, then you just take average of all those estimates and treat that as your limb length of j, and that is what is equal to half of d I j plus delta I j. Okay. In a similar manner, you can also set limb length of j. Okay. It is just a similar argument. This is the reason that neighbor joining works even if d is not additive, and it is taking a very robust estimate, that is in some sense the average between all the violating leaves. Okay. It just gathers the evidence from all the leaves, and then there are some entries of the D matrix that make it non-additive. It is going to use the estimates from all of those entries and then average it. Okay. That is the idea. The idea that if the input satisfies certain assumptions like additivity, what is a good algorithm, right. So, if the input satisfies an assumptions, then you want the perfect answer or perfect solution, right, that perfectly fits the matrix in this case. If the input does not satisfy, not satisfying the assumptions, then you want a heuristic way or a robust way, such as what neighbor joining is doing, right. So, it is using the average of estimates and so on. So, you want a heuristic if your input is not satisfying your assumptions perfectly. If the input satisfies your assumptions like additivity perfectly, you want a perfect answer, in the sense that a phylogeny or a tree that perfectly fits the matrix. Okay. So, this kind of strategy of a good algorithm where you have these two scenarios may be useful for other settings as well, okay, other problems as well, even outside biology or bioinformatics. Okay. Let us come back to this which animal gave us SARS. So, the neighbor joining and coronaviruses gives this particular tree, and still human and palm civet are closer to each other, and then you have these other trees, and this is now applied on the original non-additive input matrix. Okay. And this consistently shows that palm civet may have been the origin of humans, right. And then you can also look at expanding it on all the different samples that was identified in 2003 when there was this outbreak, right, in the Guangzhou province or the Zhongshan province or Hong Kong in China, right. So, in these provinces in China or in Hong Kong, and you can see here that this palm civet is related to this Guangzhou one, right, and then there is another Zhongshan province where they found another viral sequence which is close in similarity to palm civet. And so, all of that, like I said, the current understanding is that the bats are the reservoir of these SARS coronaviruses. So, that is one of the theories that are being put forward, and then from there it may have jumped on to palm civet, and from there from palm civet to these specific individuals in who are some of the early cases of infection in this 2003 pandemic. Okay. So, here we are looking at just one of them, but we are now expanding this human into multiple human individuals from which this SARS coronavirus has been taken, and then this palm civet is very close to many of these human samples. Okay. These people may have gotten the virus by when the virus jumped over from palm civet to these individuals in these provinces. Okay. Okay. So, we have so far looked at distance based phylogeny. If you have a pairwise distance matrix like all species versus all species, n species meaning n by n distance matrix, we have additive phylogeny algorithm, we have the UPGMA clustering heuristic, and finally, the hybrid best of the two, the best of both worlds Neighbour-Joining algorithm, right. Now, but none of these algorithms tells you what the common ancestors are, right. So, what is the sequence of the common ancestors, what are the states of the ancestors in these phylogeny. We only observe the sequences at the current day species, because we can't go back in time and get the sequences of the ancestral species. But can we use the power of computation, right. So, can we use computational and statistical modeling to actually infer what might have been the sequences for these common ancestors. Okay. We will take a purely computational approach based on the idea of parsimony, okay, and we will see what that is. Okay. So, we have lost information when we converted a multiple alignment to a distance matrix, right, and all of these sequences are gone, but can we now reinsert these sequences into the leaves of the phylogeny and then start guessing what the sequences would have been at the internal nodes of the phylogeny. Okay. So, we started with the chimp, human, seal and whale. We looked at their sequences of some gene, let us say. We looked at what are the distances between them in terms of the substitutions, right. We found these things, and then we found the phylogeny. Now, can we add back these sequences and try to say something about these characters which made up the distance matrix, okay, or the states which make up the distance matrix, and that is what we mean as the character based tree reconstruction.